First of all, thanks to the organizers and thanks to you for gathering to listen to me online. I hope you enjoy the discussion and also a little bit of the beach. So I'm going to talk today a bit on a subject which is different from the subject of the previous talks. I'm going to talk about collective modes in third harmonic generation in the context of the unconventional superconductor, but we'll mostly be talking about the iron-based superconductors. And so what I'm going to present is a summary of 3 publications that you can see. If you want to look for more details, you can look in these publications. Now, the work that I am going to present has been done in collaboration, which basically with my PhD student, Marvin Müller, but we also benefited from the discussion with our former colleague, postdoc Pavel Volkov, who is currently at Rutgers University, and Indra Neil in Paris Diderot University. Okay, now let me start with basically reminding you about the type of collective excitation if you are talking about conventional single-band superconductor. Okay, you have a charged superfluid breaking a U1 symmetry, and you get a new ground state, which is described by having a finite order parameter. This typical Mexican head potential should have you 2 kind of modes. So one is the amplitude mode, which is in this case called the Higgs mode, while you also should expect to have a phase fluctuation, so basically moving along the minimum of this Mexican head. But the point is that because you're dealing with the charged superfluid, if you perform a gauge transformation, so if you start from your free energy functional and you start to perform gauge transformation, in this case, it just turns out that in this case, your phase get more or less eaten up by the vector potential. Because now you need to include also vector potential in the configuration because you have to complete the charge. And then what happens that after you perform a gauge transformation, your free energy functional contains essentially only the amplitude fluctuation. The phase fluctuation get eaten up by the vector potential. Now, if you also include the long range Coulomb interaction, you can show that what you originally called the phase fluctuation becomes now a plasmon, but essentially it just tells you that if you are looking into the single band superconductor, the only collective mode that you can see is the Higgs type, so the amplitude modes. Now, the other little problem, if you want, is that if you look again in the equilibrium, you see that there is non-linear coupling between the vector potential and your Higgs mode, which is essentially tells you that the problem is that you can't really see this in a linear response, except that you do something. For example, the first time the Higgs mode was observed in the linear response was in the Raman spectroscopy in a superconductor, which also has a charge density wave. And because of this additional breaking of the translational symmetry, you can couple your amplitude fluctuation to the vector potential linearly. But you can go now to the third harmonic generation, and in the third harmonic generation, because you can excite with your pump pulse your Higgs mode, and then you can get the coupling to the vector potential now in the third harmonic generated currents, and that's actually the whole excitement about the real Schumann experiments. Where they have observed that in a pump group setup, you can indeed excite these modes in one of these niobium nitride superconductors. We have shown that you can generate, if you apply a pump pulse, which is much smaller than 2 delta, and a probe pulse, which is much larger than 2 delta, you can essentially excite oscillation of your conductivity by which frequency, if you do a Fourier transform, is exactly correspondent to the 2 delta. One has, however, to mention at this point that the story is actually not that simple, and the interpretation of the third harmonic generation experiment appears to be still a little bit ambiguous. The part of the problem is that if you look into your Higgs mode, its energy position is 2 delta. However, you also know that you can break Cooper pairs and generate quasi-particle continuum, and its energy is also proportional to the 2 delta. And in principle, there will be a contribution to the third harmonic generation current, which comes essentially from the dispersion, which of course also have quasi-particle, and if you break your Cooper pairs, the 2 delta will appear there, and that has been shown by the work by Lara Fitzpatrick and collaborators. But actually, if you do the honest calculation, at least in the clean limit, you actually can show that the contribution of this for the particle continuum, which will also be essentially at the two delta, is 3 orders of magnitudes higher than the actual contribution of Higgs mode. So, which essentially raises again a question: what is experimentally seen? And then it's still an ongoing discussion, but essentially the answer is that the problem appears in the clean limit, but if you go to the dirty limit, if you introduce magnetic and non-magnetic impurities, include the retardation effects, that may essentially change the balance between this charge density fluctuation contribution and the Higgs mode. But from a point of view of experiment, you see the oscillation at the 2 delta, and you can still call them the Higgs mode, although in reality that just has to do also something to do with breaking of the Cooper pairs into the quasi-particles. Anyway, now let's ask a question about the unconventional superconductor. And let's even assume that you are essentially dealing with essentially an S-wave superconductor. However, what is important in my case is that one of the definition of the unconventional superconductor is not that it breaks an additional symmetry, but essentially is that the mechanism is non-phononic, which basically means that there is a mechanism which is, for example, a repulsive mechanism, and the most, let's say, common example is that you are dealing with some density fluctuation, charge or spin density fluctuations, and these fluctuations work. You can go back down to the Conan-Luttinger, who first looked what will be the contribution of the particle Hall instabilities into the Cooper channel. And what we know is that, and this has been done on the basis of the Hubbard model, and what you can show in this case is that, in a great example, that now your pairing problem becomes a convolution between the Fermi topology that you have, which is, for example, here the situation of the cuprates, and your basically spin susceptibility in this case, or your susceptibility, your instability in the particle Hall channel, and provided that you have a large density of states here and the peaked fluctuation spectrum at the pi, it gives rise to a D-wave superconductor. And in the Hubbard model near the Hubble. But what's important that if you now study the entire phase diagram as a function of your filling and function of your for example, your T prime, which is an additional parameter on the model, so the hopping not only between nearest but also next nearest neighbors, you can find out that it's just a coincidence, particular coincidence when your spectrum is peaked at pi is that you get D-wave superconductor, but actually you have all the other states which will be, for example, extended S-wave, dxy, and so on. So you always have some secondary instability, which is even present if the D-wave ground state winning. So you can ask, can you see this subdominant mode also in the non-equilibrium, and do they give a signal to the short harmonic generation? And this is actually something that I'm going to address in the rest of my talk. Now let me concentrate for the sake of simplicity on the one particular mode, and this has a name of the Bardasov-Schrieffer mode. So imagine again you have a unconventional superconductor, but still, like it is a situation in the iron-based superconductor, we believe that the ground state still an overall A1G symmetric, so you can dub it as an S-wave superconductor. However, it is driven not by the attractive electron-phonon interaction, but kind of spin fluctuation or density fluctuation pairing. And however, what we also know that in the superconductors, you also have a subdominant channel, which is a D-wave. And if you are in the situation when the S-wave is ground state, so it means that your instability in the D-wave loses. However, you still have, even if you have an S-wave ground state, you still have a residual attraction in the D-wave channel. And it is known, and this goes back to the work in 1961 by Bardasov and Schrieffer, that you would expect to see some collective mode. And these collective modes I also appear in the linear response. Okay, so for Q equal to 0, they do not couple to the electromagnetic field because uniform field cannot change the internal structure of the bound state. So it's like an exciton excitation inside the S-wave ground state. But once you introduce some non-uniform, like for example in the Raman scattering, you can couple to this mode. And then also another interesting suggestion that once you have a disorder or you have a supercurrent, then you can also observe this mode in the linear response. And but particularly interesting this becomes because if you have a particular symmetry of the Raman response in B1 gene, you should be able to see. And that's indeed something that is believed to be observed. For example, this is an experiment on the 1 to 2 optimally doped, where in the B1G you see some particular collective excitation in the B1G symmetry, and the corresponding theoretical analysis suggests that this might be a Bardessa-Schrieffer mode. The same type of excitation has been observed in the electron intercalated iron selenium more recently, and also there are measurements in the 1144 compound, which all see that there is enhancement of the collective excitation in the B1G channel, which basically under the assumption that the ground state of the superconductor is A1G, so it's still S-wave, then what you see is actually a Bardessa-Schrieffer mode. Okay, so then let's try to see what's actually happening on the ground. Okay, so one way of doing it is you can introduce the Anderson pseudospin theoretically, so this means that you can so this is one of the simplest way to treat your system out of equilibrium. So you treat your BCS type of the Hamiltonian with the help of the pseudospins. So where you introduce that your Cooper pair is basically can be described as S6 and SY type of spin operator, pseudospin operator, and your SZ is a change of the density. For the particle density, and then essentially by introducing an non-equilibrium, you introduce a sort of your BCS Hamiltonian becomes a usual, if you want, Landau-Lifshitz type Hamiltonian, and once you introduce a non-equilibrium, you can do by introducing a parallel substitution, you basically quenching your Z component of your pseudomagnetic field, and by doing this, your pseudospins start to precess, and from there you can extract the information about the Higgs mode. And this is something that has been again known for decades, and this is one of the first works along this direction, which is done by my colleague here in Bochum. But at that time it's the Soviet Union who has shown that in this case your Higgs mode starts to oscillate, and because again you still have a damping for the quasi-particles, even if you don't have itself. Now imagine, can you really excite excitation? So can you excite a Bardessa-Schrieffer type of mode? You can immediately do this by simply looking into the symmetry analysis. What you basically need in order to do this, you need to decompose your pseudomagnetic field into the reducible symmetry representation. And in a tetragonal system, you need to show that you have to have a B1G. And then what you need to show is that once, if you want to excite a D-wave type order parameter in the S-wave ground state, you need to show that indeed you can decompose your B1G out of your electromagnetic field, and once you have a polarization of the field which is not along the diagonal, you can immediately excite your D-wave order parameter. And this is exactly what you see. So it's exactly the same analysis. You start from the ground state, you start from the S-wave ground state, and what you immediately see is that in contrast to the single band S-wave case, if you have a D-wave subdominant instability, you start to see, in addition to this simple oscillations that you saw in the S-wave case, you start to see this additional modes and irregularities, and once you do a Fourier transform, you clearly see that your oscillations are dominated by the two frequency. One of them is your Higgs frequency, and another one is your Bardessa-Schrieffer type of excitation, which you can clearly identify, which you clearly see by
Sorry, 5 minutes left.
Only 5. Okay, then let me now continue. You can analyze this, and the first thing that you notice that because your Bardessa-Schrieffer mode is well below the continuum, it will react to the additional fluence change quite differently from the Higgs mode, so it will be first staying constant. And but of course, you can say at this point that it has using Anderson pseudospin works very well for the neutral superfluid, but we have now a charged superfluid, so you need to take careful and introduce the Coulomb repulsion and treat it in the gauge invariant formulation. This you all can do by simply using an effective action formalism, by doing a set of point, introducing Gaussian fluctuation, by integrating out your degrees of freedom, by getting the corresponding information about the collective modes in the system, and finally the electromagnetic response. So let me skip all the details. And essentially, the way you do it in experiment, you perform a measurement of the total current as a function of temperature. And essentially what you do is that in this case, once you hit your collective mode, which is either Bardashev-Schrieffer or Higgs mode, you start to see a peak in the third harmonic generation current. Now, this is how the picture look in the case of the usual Higgs mode, but once you have a subdominant Bardashev-Schrieffer mode, you start to see that you actually will develop a two peak, you will have two contributions, one which is coming from but what is important in this case is that the amplitude of your Bardashev-Schrieffer mode will be of the same strength and even stronger than your charge density fluctuation. So you don't really need to introduce impurities, magnetic or non-magnetic, to strengthen the contribution of the Bardashev-Schrieffer mode. And this is exactly what is the advantage here, is that you will see the signal even in the clean case. Other important part is that you will see it not only for the parallel, but also for the perpendicular direction of the current. You can do the full polarization analysis, and this is also something that will help you to see this experimentally. And now let me just spend the last 2 minutes on another question. Now, somehow you would say, okay, this is an interesting question, but at the end of the day, how many systems we have where we have a coexistence or competing of the D wave and the S wave ground state? Now, my statement will be that yes, this is maybe relatively rare. You need to look for a specific example. But we have a lot of, also most of this unconventional superconductor show also instability in the other channel. And one of the instability is the nematic channel. And now, if you look more carefully in this nematic channel, it actually turns out that nematicity and Bardashev-Schrieffer has something to do with each other. Because the nematicity, what the nematicity tries to do? The nematicity tries, so basically this is a breaking of the tetragonal symmetry in favor of thrombicity, and it likes to favor an S plus D mixture. While Bardashev-Schrieffer mode is in principle a signature of S plus ID state, because once your Bardashev-Schrieffer mode condense, you form a time reversal symmetry broken state, which is a so you can elaborate on this and try to see, can you actually have a situation when you have nematicity, D wave and S wave ground states, and they all compete with each other, and you try to see whether you can have a Bardashev-Schrieffer mode even in the situation when the secondary instability is weak in the D wave channel, but you have essentially nematic. And the answer is yes. So essentially, even in the situation, then when the interaction in the Bardashev-Schrieffer mode is repulsive, so it means you won't see this mode because it will be in the continuum, but you have a strong instability in the nematic channel, you will suddenly see a feature of this Bardashev-Schrieffer mode in your third harmonic generation experiment, which in this case can be not called purely Bardashev-Schrieffer mode, but essentially Bardashev-Schrieffer nematic mode. And this you can analyze in the context of the S wave ground state, but you can also analyze it in the context of the D wave ground state, because you can show that you will see additional modes in this place. So our main result is that secondary mode, secondary superconducting instabilities will be stronger, will give a strong smoking gun. They should be visible, and moreover, this Bardashev-Schrieffer type of excitation will basically mimic, or essentially the nematic instability will show up itself as a Bardashev-Schrieffer secondary mode in this experiment, which in this case will be a strong signature of the nematic fluctuation. And at this point, I would like to stop and thank you very much for your attention.
Thanks, Ilya, for the nice presentation.